Thank you, Guan, for the thank you for the invitation. Thank you for the introduction. Hello, everyone. Good afternoon. It's a pleasure to give this talk today at my alma mater at University of Buffalo. Myself actually started my graduate studies at Buffalo as well. I have a master's. I had a pleasure to do research at UB for 3 years. Then I moved to Northeastern to finish my PhD, and now, as Professor Guan mentioned, I'm a research assistant professor here. So today, I would like to talk a little bit about one of our latest works, which has been published recently in IEEE CCON. I work with a great team here at Northeastern with Kerem Enoş and Deniz Ünal and Thomas Melodia, which basically we've been looking into this exciting work for quite a while at this point. We actually have quite a bit of work that is around this, but we were always having this gap between underwater and aerial drones, and that's why we actually really were interested in this talk. So let me give you a little bit of motivation. Why do we need to have a communication network, or why do we need some sort of a visible light networking between aerial drones and underwater drones, and why it is actually a challenging problem? So the motivation is basically, you all know that there are billions of applications at this point for aerial drones. We have it in our daily lives. It's getting more prevalent every other day. And underwater modems is also picking up quite a bit lately for many different applications. Yet today, if you want to deploy a network of sensors composed of autonomous and mobile and wirelessly connected aerial and underwater assets in different domains, this is not possible, even though this can actually, this kind of a technology can play a key role in many applications. The applications that can come to mind first is like offshore oil and gas exploration. You can have infrastructure monitoring. You can have tactical surveillance. You can have environmental monitoring. And once you have these distributed assets in multiple domains, acting in unison and accomplish a common goal, this actually be a very strong tool for many different applications. Yet, if you look at it, what is out there today, there is no easy way to establish a high data rate, robust, bidirectional communication link between an aerial and an underwater assets. The most common way that we use today is we deploy buoys. We basically have these floating devices that has RF communications, which is the most common technique that we use for aerial drones and for terrestrial networks. And then we use acoustic communications in underwater, which is the most common and most effective way of communicating in underwater with different communicating assets in underwater. So what we have done is we basically have these floating devices, has two different communication interfaces, and we were bridging the gap between an aerial drone and an underwater drone. The thing is that in order to have such a deployment of a large deployment of networks, or if you want to have a network that is moving from site to site for doing a different application, you have to have multiple floating buoys. So you need actually infrastructure similar to a base station you can think of. You need some sort of a backend to support this communication. And this could be a problem because then you need probably millions of floating buoys if you want to cover the 75% of the planet, which is covered by oceans. The other thing is that these floating devices, even though in a controlled environment, you can think of, okay, we can deploy them into the, closer to the shores, we can deploy them into the ports, we can deploy them into the base. So the things there where we can control them. Or we can just basically cover some areas, so we can just say that, okay, for the rest, we're not gonna interested in this technology. But even for these controlled environments, there are some downsides of these floating devices. They're actually quite vulnerable to the environmental effects, meaning that if there is an ocean dynamic, if there's like some sort of a hurricane, storm, these floating buoys tend to be perished. They are basically taken away with the current. And another thing that about this is they're quite non-secure. So if you want to do some military applications, or even if you have a critical assets that you need to communicate at all times, these devices can be easily detectable, they can be jammed, and actually they can be deactivated. And you don't need a high tech to do that, actually. I actually have a news here that's showing two fishermen just basically steal one of the US government ocean science buoys, and they want to sell it back to the government. So they're quite vulnerable. You can just go there and pick up with your boat, and there is no way to secure all of them, or there is no way to guard all of these buoys. So you can basically lose your communication link quite easily. Also, these devices turned out to be quite inefficient and costly. So if you want to buy a buoy off the shelf today, they will cost tens of thousands of dollars, and they will be very heavy devices. They will be very hard to deploy. They will require some quite large moorings, which we're talking about hundreds of pounds moorings here that you need to deploy into different parts of the oceans. So researchers were looking at different options, and the first thing that was coming into mind, can we just use autonomous surface vehicles? So can we just have some sort of floating, but the buoys that we can control, or can we have some unmanned underwater vehicles that can submerge? Even though this actually elevates the problem a little bit, they still tend to be very inefficient, because this means is that that device that you're using always need to resurface. They need to always act as relays. So there's always some sort of inefficiency in the communication channel. So what we were looking is how we can come up with this problem and how we can actually offer a solution. First, we basically went to the current state of the art. We see what is out there, what people were doing for communicating across this air-water interface. So most of the works were focused on using laser light. So these are like diffuse lasers, or like very precise alignment lasers. In most of these cases, the lasers actually work in one single direction. It's unidirectional. So it works from an aerial drone to an underwater drone, or from an aerial asset to underwater asset at this stage. And most of these works, if you look at them, these works that is published, they're actually used in a very controlled lab. So basically, they've been tested only in some sort of a test tank. There were no channel effects. There were no waves. There were no any current, any effects that you can have it in a normal ocean environment, even in a very nice weather day. That's why we decided probably optical, while optical would be a good solution, lasers may not be the best solution. That's why we start looking into the LEDs, which are basically visible light communication technology, which doesn't require that precision, can be much easier to detect and much easier to actually control. But I will come to that. I would like to show a few other alternative approaches that people were looking into. So one work that is from a colleague in MIT that published, I think, a few years ago and get quite a bit of actually interest from the community was something system, they called it TARF. So TARF was a translational acoustic RF communication. So what they were trying to do and what they have showcased is basically they were putting a acoustic speaker underwater. They were basically sending acoustic waves. They were creating vibrations in the surface, and they were detecting surface vibrations with a radar. And in this way, they were making communication from underwater to the air, which is basically can only work with one direction. While this is actually quite a different approach from what is out there and quite interesting, it was kind of limited in operation. So it can only work in surface waves that are less than 60 centimeters, which kind of intuitive, if you think of it, you're looking into the vibrations on the surface. And once you start having a very big surface wave, these vibrations will tend to basically integrate into that surface wave, so you will lose your data. So you can think of it from a signal processing perspective. You have a very high noise carrier in the same band with your signal, so it's getting harder to detect it. Or else you have to have some sort of a bandpass filter, which is not really possible to have it on a surface, an actual mechanical wave actually. These communication methods also tend to be very low rate. It can do only 40 bits per second. And it also requires quite a bit of precise alignment between this radar and the sound vibrations speaker. The other thing, another approach, which actually has been quite heavily worked by Dr. Sunji in Buffalo, actually, is a magnetic induction. So magnetic induction is another technique that is heavily used for boundary, or like, as they call it, multi-medium communication. So if you want to go from underwater to the air or underground to the air, this is a very common method that is being used in some research projects. So this actually offers some promising results. However, the communication can be very limited in terms of range and capacity, because it actually getting quite high attenuation from the salty water, because these are still magnetic waves, like RF waves. They don't tend to really work in the underwater side of things, even though they work fine on the RF side of things. So after looking at these alternative approaches, we have seen that there is no one single approach that can work in both directions. So you cannot use the same interface communicating from one side to another, from air to the water or air to the water. So you cannot cross this interface from both sides. There is no effective way to do that. And if there are some ways, they're pretty much very limited, or they're very much requiring precision for their approach. So what we have looked is to make a system that can go bidirectional. It can enable links through the air-water interface. It does not require any relay nodes. And we would like to do that in a software-defined fashion. Why we want to do that in software-defined fashion is probably, I'm sure that Dr. Guan explained you what is software-defined networking, how is this actually affecting the whole 5G, 6G domain, and it's pretty much the state of the art at this point for many different ways of communication. What SDR gives us here is basically, it is giving us the robustness, secureness, and also a capability to program the nodes and self-optimize based on the channel at real time. So once you have everything programmable, thanks to this software-defined approach, you can actually change your communication protocols, you can adapt to the environment, you can change the beam patterns, you can do beamforming. So you basically have quite a bit of tools in your arsenal to really get a reliable communication through this interface. So the visible light networks tend to be spectrally efficient. They can do much larger coverage area compared to optical, like a standard optical lasers. They can actually reach quite a bit of communication range with, if you provide the power, it can be goes to tens of meters easily, can go up to 100 meters, which actually we're currently working on. I'm going to tell you a little bit about that at the end of the future work. And they tend to be actually quite resilient against suitable for ocean dynamics that we have seen, which I'm going to talk a little bit about that as well. So we have done quite a bit of experiments and some simulation work to mimic these effects. So what we have done in this work is threefold. What we have done first, we built a derived mathematical model. We try to characterize the limitations imposed by the water surface, distribution, optical properties, path losses. So we try to create all different layers of model, how it will affect a light beam, a light ray throughout from target to the destination, to the source, to the source and to the target. What we have done is that we built a 3D simulator using that channel model. In this channel model, we basically evaluate several parameters. We basically emulate different effects. And as a second part of the project, we basically built a software-defined visible light communication modem, which incorporating a reconfigurable SoC architecture, including an FPGA for driving the communication protocols, can also work as a software-defined radio, which I will explain a little bit. We also built visible light front ends, LED drivers, custom VGA and photo detectors to make the transmission and reception. And what we have done using this VLC modem, we have done a modulation scheme analysis in the tank. We have done channel analysis studies in experiments, and we have done also some preliminary ocean experiments in a real underwater channel. So first off, I would like to describe a little bit of what is the channel model that we have built and what it was considering. So the channel model, what we're trying to do first, we start modeling the channel by modeling the surface waves here. So the surface waves generated was basically calculated by third order Stokes waves, composing of sinusoidal waves. This, I will not go into this math here. You can basically address that in the appendix of the paper if you're interested. But in the basic idea, what we have done is first we created how a surface of an ocean can move and how this would affect a light ray coming from inside the water or outside the water can be refracted in this boundary. With what angle, what you will lose. And this is the first part that we have calculated. Then what we have done is that we built a ray tracing model. So we built the ray tracing from a transmitter field view. So we basically track the races, track the rays, and based on the beam aperture of the light sources that we are using. And then we start creating a illuminated area at a depth or at a height where we are calculating how much intensity, light intensity we are receiving. So here, as a simple formula, it's kind of like a derived formula. Is basically we are calculating the received light intensity in this red position that is emitted from that blue position. So this is giving us how much loss occurred on the air. Then we have water surface loss, which is the transmittance calculated by how much is actually refracted through the surface waves and how much is actually passed through the surface area. And then we have the loss in underwater, which is calculated with the classic Baer-Lambert laws, basically how much you're losing inside the water domain. And you can basically use this in both ways. So you can calculate how much illumination you have on the air if you're emitting light from the depth, or you can calculate how much illumination you're getting in under the water if you're emitting light from the air. And then we have definitely here different distances. We can have different wavelengths, meaning that how big is the surface waves that you're calculating here. All of these are actually our inputs of this channel model here. So what we have done, we use this channel model. We built a toolbox in MATLAB. And here I would like to show a little bit of a video how this looks. So the top one is, you can see there are no water surface movements. In the bottom one, there is a water surface movement. So this is where our source is, where we are basically sending the light. You can see how rays are refracted backwards, and then how the rays are transmitted can pass. So the red ones are actually showing the transmitted rays, and the black ones are the ones that is showing refracted backwards. And this is actually a 3D coverage area. So it shows how the light intensity changes in power in dB. So this is like a normalized received power intensity. So you can see the middle point is quite intense, and then it gets quite lighter towards the edges, you can see there's like a 3 dB difference, and then you have basically a coverage area that is disappearing here. And you can see how a surface wave can affect this. Actually, let me play this a little bit, and you can see how it's affecting. So you can see while there's a surface wave, you can see how the coverage area of a LED can change. So it gets smaller, bigger, smaller, getter. So basically, even if you have an asset here, this is the moment that you will lose your link. So we believe this actually can be a quite powerful tool for not only simulating the channel, but also for future tool, so we can actually understand how we can deploy the multi-domain assets in underwater. So based on the anticipation of the channel effects and surface waves, so we can actually pre-calculate what could be the transmitting area, what will be the coverage area, what is the height that we need to put our aerial drones, what is the depth that we need to put our underwater drones. So that will give us, beyond optimizing the protocols, we can also optimize the position of multiple drone assets. So we can have this automatic swarm controls, pretty much how we can position these multi-domain assets. On the right, you can see actually how this is working the other way around. You can see how a source that is in underwater can be transmit to the air, and you can see how the transmitted rays are covering an intensity. You can see it's a little bit larger from water to air compared to air to water, and this is mostly physics of the surface waves affecting that. So this is a quite strong tool that you can put many different parameters to understand the intensity and calculate what could be the communication layer. And you can mimic the communication channel quite well. As the next step, we built a software-defined VLC modem to realize this system, and we want to see how this actually really works in a real channel. So in the VLC modem, in this tube, you can see that water tube, there is the LED and the photo detector on the end. We have three main modules in this model. So we have a main module which has a micro Z SoC. It has digital to analog converters, analog to digital converters. We have command and control of these SoC. We have data streaming and recording capabilities, which basically led us to, in real time, drive signals from MATLAB if we want to. If we don't want to create data inside the main module, we can basically easily drive from MATLAB, record from MATLAB, which is actually quite of a strong tool if you want to do some controlled experiments, especially in this stage. But going forward, that is what we're imagining, is this connection will disappear, and then that will be a standalone prototype that can do visible light communications. What we have as built here is we built also a visible light communication front end. So we have a LED driver. We have blue light LED, which basically works in 450 to 480 nanometers. We have this variable gain amplifier that is connected to an avalanche photo detector. And one thing that I guess worth mentioning here is that why do we use blue light in visible domain is basically the best light that can propagate with the minimum loss in water or aqueous media is blue. That's why actually all the water and everything is blue, because it's the best reflected light that we can see with our eyes. That's why the blue light is the most effective way to communicate visible light in underwater environment or in aqueous media, let's put it this way. So we have a power and switch module to control and turn off this system or power this system. If you look into a little bit of the specifics in the visible light front end, we have basically 4 LEDs. So we're doing some sort of a cooperative beamforming in light intensity. We're driving 4 LEDs at the same time. We have around 400 megahertz bandwidth, which in the initial test, we're only using 1 or 5 megahertz. But this also kind of gives you how much data rate you can have. And we have a voltage gain control amplifier which can go up to 50 dB, which we can digitally control from the main module. So you can actually run some sort of an automatic gain control algorithm here if you want to. So we have done 2 sets of experimental studies. We have done some experiments in the water testing, and we have done some experiments in the ocean. First, I would like to start with the ones that we have done in the test tank. So the one in the test tank, we actually use 2 setups. So we have a pre-aligned setup, which means that we eliminate any misalignment loss. And we basically put some aluminum rods to create some sort of like a virtual tube channel that is perfectly aligned between a transmitter and receiver modem here. And why we have used this pre-aligned setup, we have basically looked into the different modulation schemes. We try to assess which is the best modulation scheme in such a channel. We try to assess how surface waves can affect. We look into the background noise. We look into the effect of the water clarity. And we have a second setup where we are basically have a aerial modem attached to a crane, and then we have a submerged modem that is fastened to a mushroom anchor here. And what we have done is that we basically misalign these 2 modems between each other. We vary the distance, we vary the misalignment, so we look how it works in different distances and different misalignments. So we try to basically cover all the bases that a system like this can face in a real environment. So whatever ocean environment can bring onto a setup like this, if you have an aerial and underwater drone equipped with this communication interfaces, this is what we have tried to mimic and showcase how it is improving and how it is performing under these conditions. So the first thing, we basically look into what is the best modulation scheme that can work in this, because modulation scheme in underwater is much different from an RF channel because it uses actually positive and real values. It doesn't have coherency, it doesn't have phase information. It is using non-coherent waves. It's similar to what they call it direct antenna modulation. So you drive the LEDs, and the LEDs basically is automatically taking the signal to a carrier frequency rather than just you put them on a carrier frequency and drive it like we do it in a standard RF waves. We look into the different modulation schemes. So we look into the single carrier modulation schemes, which are the most standard used in visible light networks, especially in indoor and outdoor applications, in Li-Fi, which are like on-off keying or like on-off keying with Manchester encoding. We also look into this more novel techniques, multi-carrier modulation schemes. So we look into the carrierless amplitude phase modulation, cap modulation, and different layers of cap modulations, MCAP modulations. We also study and look into the optical OFDM methods. So there is the DC bias OFDM. We look into the basically the clipped OFDM, ACO OFDM, and the flip OFDM. So these are different varieties of a standard OFDM that carry phase offset. So these are non-coherent OFDM methods, which basically mimicking a multi-carrier system with some spectral efficiency. So we generated all these communication schemes in MATLAB. We created those and then we fed them into the FPGA for driving the SoC and the visible light modem. For all the experiments, we have used the standard 1 megahertz bandwidth. We use a standard VGA gain, and we try to compare all of these different methods because these are quite different from each other. But what we have tried to fix is we try to fix the spectral efficiencies of each. So we try to compare them at spectral efficiency 1 and spectral efficiency 0.5. So these are the kind of how we select the possible modulation order. Let me show you the results. So we have done quite a bit of experiments in different environments. So we first look into the air to water with a spectral efficiency of 1, and where we have a target, where we have a source that is at 0.35 meters, and then we have a receiver that is at depth of 0.55 meters. We look into the different communication methods, how they're performing, how is their bit error rate performance for different SNR values. So what we have seen pretty much for all different settings, both for water to air or air to water, or for different spectral efficiencies like 0.5 or 1, we have seen that cap modulation is giving us the best result. So cap modulation seems to be the most robust bit error rate, giving the best bit error rate performance based on the SNR. It actually can get smaller than 10 to minus 6 bit error rates at SNRs around 6-7 dB, which is quite of a good value. So this means is that it only wakes one error in 1 million bits, to give you a sense. And this is doing actually much better than this at this low SNRs. So we have proved that actually capped modulation turns out to be the most robust communication method. And we actually having an ongoing work to going a little bit deeper into that and seeing what are the trade-offs, how robust we can use this. So that is actually hopefully up and coming and will be published pretty soon. Then we also want to look the bit error rate from a spectral efficiency perspective. So we'd like to see if we start increasing the spectral efficiency by keeping a standard fixed SNR, how is the bit error rate changes? And what we have seen is basically once you fix the SNR and you want to start increasing the spectral efficiency, we see that actually the DCO or FDM is outperforming the cap. So this means is that even though a DCO or FDM may not offer a robust performance in terms of bit error SNR as much as the cap modulation, it can actually get you a little bit more spectral efficiency than the cap modulation once you go with the bit error rate. So there is a bit of trade-off between robustness and data rate between DCO, FDM, and cap. That's what we have seen. Just for simplicity, for the rest of the experiments where we're looking into the channel analysis, we pick basically to go with DCO, FDM, because we're also always tend to use higher data rates, which is kind of a little bit tempting to be able to get higher spectral efficiencies. So first thing that we look is how the distance is affecting. Is it actually linear? Is it actually different points, different spots that is changing that? So what we have done is basically we have an air to water channel. What we have done is basically we start changing the distance in the water and the distance in the air. So we basically start moving the source and the receiver farther from each other. You can see that at every 0.05 meters, we are losing around 3 dB. So the solid lines are the experimental data you can see. And actually what we have also done here is that we also want to cross-validate our simulation model that we have developed. So we also run some theoretical results with the exact same setup and we just compare them. And here actually we cross-validate that theoretical and experimental results are quite close in a distance manner. So we can actually simulate the distance quite well with our model, and it really, really matches to a real channel that you can mimic in a water tank. You can see the same regime is actually kind of consistent from water to air channel. Once you start moving them far apart, you start losing the intensity. And over I think this is around 0.6 meters further down compared to this point, and you can see you're losing around 10 dB power if you go through this distance. So this actually was a good practice for us once we cross-validate the simulation model, and we're convinced that simulation model will give us a good result to estimate how far we can actually move this distance between with the current energy that with the current power levels that we have, even though it's not like the maximum power that we can achieve. We have seen with the current system, we can do around 5 to 2.5 meters, somewhere there, with bit error rate less than 10 to minus 6. And this basically will get us to a 0.5 megabits per second, just over a 1 megahertz bandwidth. So if you use the whole bandwidth that is available in this modem, you can basically get close to 200 megabits per second, which quite high, very close to an RF modem. And this is all happening through the under air to water and water to air interface. So another effect that we have looked is that the misalignment. So what happens if we misalign these two nodes between each other, and how this actually compares to a theoretical value. So when you look into the theoretical value, obviously I have shown you that 3D channel model, and you can see that in the theoretical value, you have a very well-defined ranges here, because once you go around the coverage area, it just assumes that there is no refraction, there is no light coming here. But when you do that experiment in real experimental environment, you can see actually there's quite a bit of refracted light waves that is going on to the side. So you can see even basically the receiver and the transmitter pairs are not perfectly aligned with each other. You can see actually you can have a coverage area of 0.5 square meters. And this actually gets much higher if you try to go from water to air. The coverage area can go up to 1.54 square meters. So this is quite important, because by adjusting your depth or by adjusting your height, you can increase your coverage area in the water or in the air. And you can actually kind of calculate that with the theoretical model. You can assume, and actually this is a much pessimistic compared to experimental value. As you can see, experimental value is much better than theoretical value here. So this is how the misalignment will affect your channel. Then we start looking into the surface waves. We basically created 3 centimeter peak-to-peak waves in a controlled manner. We basically measured the displacement with some Arduino and distance sensors. We basically created 3 centimeters continuous waves coming here. You can see that red light, how the surface displaces, and you can see how the SNR is getting affected. And you can see even with a very large fluctuation, you only lose around 3 to 4 dB, more or less. So this actually showcases that even if you have a very large water surface wave, you will still be able to communicate through this interface. Then one of the biggest questions, and one of the things that I was really curious, is how the water clarity will affect. So what we have done is basically we created different levels of turbidity in a water channel by using a zinc oxide powder, and we basically measured the turbidity unit to give you a sense. The oceans in the worst environment, they have a 50 NTU turbidity limit. So in the most in the places that the water is not clear, that is completely blue, which are mostly happening in shallow environments, or if there is like some microorganisms living in that part of the ocean, will not exceed 50 NTU. So what we have done is that we basically start increasing that turbidity level and see how much absorbance and transmittance we are getting. So how much is absorbed by this by the water channel, how much is actually transmitted, and what is that turbidity, and then how this translates in terms of bit error rate in air to water or water to air channel. So for 0.09 NTU, which is for a quite clear channel, you can see that we can do bit error rates much smaller than 10 to minus 6. 90% of the signal can be transmitted between the across the channel. Once we started increasing that 1.71, for example, you can see visually also getting turbidity. We're still be able to get 87% of the signals. We are getting still bit error rates smaller than 10 to minus 6. Once we get 25, which start getting quite blurry and start getting quite blurry for a standard ocean channel as well, you can see that air to water channel is still much better than 10 to minus 6. And we can see that water to air channel is actually start losing a bit of a performance, which goes below 10 to minus 3. And once you go very extreme, actually, which is 70, which it's way above a standard worst case ocean channel. As you can see, you cannot visually even see there is something deployed here. We can still do 10 to -2 bit error rates in such a water clarity. So expected water clarity, actually, when we have done some experiments in the ocean, was around this. In a shallow environment, you will probably expect a NTU limit around 2 or 3. So in most of the ocean channels, the communication VLC communication method can work quite well and perform bit error rates much less than 10 to -6. We also look into the background noise, which at this, if you think from a ocean perspective, that background noise will be the sun. So what we have done, we try to mimic that sun effect, obviously by some indoor lighting in a room. So what we have done is that we have done measurements in a dark room, and then afterwards we start putting this noise source, which is kind of mimicking the sun, and creating some sort of a background noise for the channel. And we have seen that once modems are farther apart, which are around 1 meter, so once the signal is not strong enough, you can see that there is around 2 dB noise floor. And this is actually kind of consistent with what we have seen in the ocean as well, which I'm going to be showing you in a second. So in the ocean experiments, we basically did an experiment in a port with this aligned setting. And what we have done is that we look into the different modulation schemes. So we just want to see if we can establish a bidirectional link in the wild. So we just want to see, okay, now everything works in a tank. We can basically kind of mimic all the effects that ocean can introduce us, but does it actually work in a real environment? And we take that to the Boston Harbor. We basically deploy this transmitter receiver pair in different settings, in different lengths, in different SNR levels. And what we have seen is actually at 10 dB, we can do bit error rates better than 10 to -5 with using the cap modulation scheme. And by using the cap modulation scheme from water to air, we can actually do 10 to -5 and better if we have SNR levels that is above 13 dB. So this is actually quite promising and shows us that we can actually make this work in a real environment as well. And that is kind of one of the most important conclusions of our work here. So looking into the conclusions, we basically built a communication system that can enable aerial and underwater assets to establish a bidirectional links and can create multi-domain swarms without requiring any relay nodes in between, like buoys. We basically built a mathematical model that we can consider and introduce water surface distribution, optical properties, path losses. We drive all this mathematical model and build this 3D channel model and a simulator around it as well. We built also the software-defined visible light communication modem, which at this point was mostly used as a tool for recording and streaming ready-made waveforms that we have created in MATLAB, but we are basically we're currently deploying them as prototypes by themselves. So where the main module is actually running the communication module, the communication protocols using the FPGA that is on this SoC. So they are basically converting into standalone prototypes. We're also done extensive experimental evaluation. We try to cover all the bases, what ocean can introduce to us. And then we have looked into different modulation scheme and look into the channel analysis, and we try to cross-validate our model with the real data. So the future work, obviously, we're looking at how the VLC modem can increase the bandwidth, data rate, how we can go longer distances. And as I just mentioned, how we are implementing those different communication schemes in FPGA. We're also interfacing the modems with unmanned underwater vehicles and aerial vehicles. Actually, on here, you can see we have the modem integrated into an aerial drone, and then we have basically a static node here where we were actually creating visible light networks in the air just to basically trial and error how we can carry those with an unmanned aerial vehicle. And then we're also currently working on how we can put that into an actual underwater vehicle. And this is going to be our next step, that we will be doing the same experiments with 2 mobile nodes in the ocean. And here, actually, we were able to create links around 15 to 20 meters height in a quite sunny day, which was really, really promising as well. And hopefully we can share these values and results quite soon with the community as well. With that being said, happy to take any questions. And once again, thank you for inviting me. It was a real pleasure to talk to you tonight, with this afternoon with you guys. Yep.